Okay, so the goal of today's class, the major one, we will have to introduce capacitance, but most likely this will be done in the second half of the lecture. We still have a few interesting ideas to discuss about the connections between the electric field and the electric potential. You remember, we're almost done discussing this scalar approach to address problems in the world of electricity, right? And now, in the previous class, we were discussing these bridges, how to move, for example, from the electric field to the electric potential. Okay, guys, I see that you're sending something in the chat. No, I cannot read right now, right? So I will address that later. I will look at that later. We discussed how we can move, for example, from the electric field to the electric potential. And we derived this formula, this integral, right? And of course, instead of taking this integral, we calculated area under the curve, E versus X in our one-dimensional cases. Then, if we wanted to move backward in the opposite direction, so if we wanted to move from the electric potential scalar quantity to the electric field vector quantity, we had to just look at the slope of the curve V versus X and add minus, so negative slope. Or from the mathematical point of view, we can say that we have to just take a derivative and don't forget a minus, about the minus, right? Okay, so most of you practice that in your recitation classes. Some of you will do it today. Right? Some of you will practice this in the afternoon. Okay, so that's what we introduced in the previous lecture. And now the question for you. We discussed very similar question in our recitation classes, right? But I want to repeat it one more time because it's my favorite question, my all-time favorite question. Because in order to answer this question, we need to put lots of simple steps together in the proper order in order to answer this question. And of course, in a month, I will probably tell you easier way to analyze this question. But for now, I want to do it hard way. So what do we have here? You see, we have information about the electric potential. So V, right? V versus X, right? And you see how electric potential changes with position. Then we'll take an electron, negatively charged object, right? And position it at this point 2, right? And release it. So initial velocity is 0. And we need to answer the question, what happens to this electron right after being released? So basically the question about a direction of motion. So will it travel to the right with constant speed, maybe right with acceleration with increasing speed, or maybe to the left with constant speed, or maybe to the left with increasing speed? Right? So we just need to answer the question, what happens to this electron, right? Right after a release. Right? Okay, so give it a try, right? And then I will discuss the way I wanted to discuss it, right? The hard way. So the poll is in the chat. Okay, now I can look at the chat. Just you need to scroll. Wow, there are so many. You already posted a few messages. Just scroll it up. You see the conceptual question 1. Concept test 1, February 23rd. Okay, and let me look at your answer. I see. And a few times I gave a question similar to this on the exam, usually somewhere on the final exam. And plus, why I like this question, because there are plenty of physics to discuss, not just one piece of physics, but many interesting concepts. Okay, I see you're still answering. Okay, it looks like we've reached saturation, no more responses. Okay, so then let me discuss it. So let's start from the very end. First of all, I want to build sort of like a skeleton of the solution or train of thoughts. And then, yeah, we'll start from the end and move to the beginning. All right, and then after creating this skeleton, we can follow the steps, right? Completing the solution. Okay, so the final basically a point. We need to find a direction of motion, right? So we need to find a direction, and then along this way we will also realize that acceleration is there. Okay, so we need to find information about the direction of motion of this electron. Okay, direction of motion, how can we get that? Direction of motion, it's basically part of the world of kinematics. You remember physics 1 kinematics, right? You remember that there are 3 levels in the world of kinematics. First level, it's a position. Second, velocity, and then acceleration. So there are 3 levels, and of course you can move up and down between these 3 levels. So direction is basically, you need to look at what happens to the position in time. You just need to look at the dynamics of the position, right? So if position, let's say x increases, so it means it moves in the positive x direction. Decreases, it means it moves in the negative x direction, right? So you just need to know what happens to the position in time dynamics. Which quantity describe that? Of course, velocity. So velocity will give us all the time direction of motion. If velocity that way, so that's the direction of motion. If velocity this way, that's the direction of motion. Period. No alternatives, right? Velocity gives us direction. But in our case, the electron is released, so velocity, initial velocity, is 0. And we want to get information about the direction of motion right about the electron was released. So velocity cannot give us an information about the direction of motion because it's 0. Okay, so what can be done in this case? If we cannot get information about the direction of motion from the first level position, from the second level velocity, we just need to dive deeper into the acceleration level. But with acceleration, we have to be careful because acceleration doesn't give us a direction of motion all the time, only under certain conditions. Simple example, let's say you drive the car, right, like 55 miles per hour that way, and you press the brake. What happens? You still move forward, still in the same direction, but your acceleration is in the opposite direction because you are decelerating. So you see, in this case, direction of acceleration doesn't give us direction of motion, right? So with the acceleration, we have to be careful. In our case, since initial velocity is 0, and you can easily imagine, for example, right now I'm standing and my initial velocity is 0, right? And if I start accelerating that way, that will be my direction of motion. In this case, direction of acceleration gives us direction of motion. And let's say I start accelerating this way. Okay, so immediately direction of acceleration gives us direction of motion. So in this case, when the velocity is 0, direction of acceleration does give us a direction of motion, right? But of course, in general, with acceleration, we have to be careful. But in this particular case, acceleration works great. So in order to get direction of motion, we need to get information about the acceleration first. Then, next, in order to get information about the acceleration, what do we need to know? Force, in this case electric force, so that we can use Newton's second law to make this transition, to move from the force to the acceleration. Okay, so the next the step before this. So what do we need to know in order to get the electric force? Electric field, right? You remember that formula, F equals Q times E. So in order to get information about the electric force, we need to get information about the electric field. Okay, and now the last step, or maybe actually it will be the first step. What can we get information about the electric field from what is given? Yeah, we have information about the electric potential, but we just established bridges, and I reminded about them in the first slide. Now we can easily get information about the electric field from the electric potential. And of course, that bridge is E sub x equals minus dV over dx. So this is the skeleton of the solution. So there are like 1, 2, 3, 4 steps that we have to make. All right, carefully. Okay, so now once we have this skeleton, so now let's make these steps in order to get the correct direction of motion. All right, so let's start with the first. We need to look at the slope of dV over dx, and of course add the minus in front. Right? So on the curve, you see, since this graph goes down, right, it means that the slope is negative. Slope is negative, and since we have a minus in front of dV over dx, right, you see minus. So minus and minus give us plus. So it means that electric field is positive. What does it mean, positive electric field? Electric field is a vector. Positive vector just tells us that it points in the positive x direction. All right? So positive x direction, it means it, in this case, it points, okay, it will be to the right. Again, every time I'm confused when I lecture, left and right, because there is a screen in front of me and everything is flipped, right? Right. So yeah, it looks like it's right. Okay, so positive x direction basically, right? So you see, this is the direction, right? And I can also show it on this graph. So that's the direction of electric field. Okay, so we made first step. Then the second step, direction of the force. Since charge is negative, right, you see Q, since it is an electron, charge is negative, so direction of force will be opposite to the direction of the electric field. If electric field is to the right, force will be to the left, in the negative x direction. All right, okay, so the force will be to the left. Okay, and now next step. Okay, I can probably show it also over here. So force is to the left. Then next step, using Newton's second law, mass can be only positive. Mass cannot be negative. So direction of force gives us direction of acceleration all the time. All right, so it means that if force is to the left, then acceleration is also to the left. All right. And as we discussed at the very beginning, direction of acceleration, in this case, give us direction of motion. All right? Okay, so as a result, direction of motion is, okay, this electron is going to move to the left. Then, with constant speed or with acceleration, our acceleration is going to be a non-zero, right? So because the slope is not zero, then as a result, electric field is not zero, electric force is not zero, acceleration is not zero. It means that electron is going to travel to the left with acceleration. It means that with increasing speed. So as a result, the answer is option E. So it travels to the left with increasing speed. Let me check which answer you picked. Majority of you, because I forgot. All right. Yeah, most of you picked this answer, right? Okay, so you see um, why I like this question, because plenty of physics from the past can be discussed, sort of like a big summary, right, of almost everything that we've discussed in this semester and some of the stuff from physics 1. That's why it's my all-time favorite question. Okay, so now
So would this be analogous to a velocity versus time graph essentially, or a kinematic graph, since it's basically a non-curved slope would mean acceleration?
no, it has it's no, I don't think that there is that direct correlation between graph, which graph you said, kinematic graph?
So velocity versus time.
No, it's more complicated than that. You cannot just say compare that graph with this graph. No. I wouldn't say. You um, actually you cannot even plot velocity versus graph. No, if you have if you had the whole yeah if you had the whole information about the velocity in time, yes, of course it will be, you will be able to see the direction of motion, but in this case we don't have that. Right? So in this case it's more complicated. Okay, so next I need to press on the slides. So we are still connecting, right? We're almost done connecting, right? Electric potential and electric field, right? We derive those formulas, bridges. How can we get electric field from the potential, or the electric potential from the field, right? So we know that. Now, but what about um, getting some quick information about the electric field if, for example, bunch of equipotential lines are given? You remember we can visualize electric potential by drawing equipotential lines. And of course, we can visualize electric field by drawing electric field lines. So what if we have, for example, a picture like this? I took it from the book. You see, we have a bunch of these green dash lines, equipotential lines. Right? You see here V plus, it means that here potential is higher, maybe let's say 5 volts. And here V minus, it's a line where potential is lower, maybe let's say 2 volts. Right? And so how can we get information about the electric field? But when you have equipotential lines, when you have some information about the electric potential. So how can we get information about the electric field from pictures like this? Quick information without diving into those formulas, right? And let me state 3 most important pieces of information that we can extract from the picture like this. And then we will look at one of the additional clicker questions, right? Today there are plenty of them. Okay, so first important piece of information. Electric field, again, electric field, E, is perpendicular to the equipotential lines all the time. If electric field, and of course electric field lines, are not perpendicular on your picture to your equipotential lines, it means that there must be something wrong with your description. Right? And even you remember, right, when we were discussing, let's say, electrical aura created by a point charge, right? Point charge creates an electric field, right? Of course, electric field we described using electric field lines. And electric field lines, you remember all the time, they are radial, right? Radial with the center, and they start on the charge. But what about equipotential lines? Equipotential lines are circles, right? Equipotential lines are circles, electric field lines are radial, so of course they are perpendicular to each other, right? At any point, the radial direction and the circle perpendicular to each other. Again, all the time, electric field lines and equipotential lines are perpendicular. And that's what we're stating here, right? Electric field must be perpendicular to any equipotential line. Okay, to the equipotential line at the point, right? At the point. Okay, so that's the first statement, and we're going to prove it in a second. Okay, in a couple of minutes. Right? Then the second statement. Electric field direction, it points downhill of the electric potential. You see here electric potential is higher, V plus, and then as you move that way, electric potential is going down. So you see that here it's a V minus. And you see electric field vectors, right? They point downhill in the direction of decreasing V all the time. Just like rolls like a ball right down the hill. And the last important piece of information that we can extract, the electric field strength. You see here, density of equipotential lines over here at this point is the highest in the picture. As a result, you see electric field is the strongest. Then here, density of these equipotential lines is the smallest. As a result, electric field is the weakest. And of course, here it's sort of in between, right? So electric field, strength of the electric field is proportional to the density of lines. Usually I state it this way. The book states inversely proportional to the spacing between lines. But I usually, I like it. I like when I say, okay, I prefer saying that proportional to the density of lines. Density is larger, electric field is stronger. Density is smaller, electric field is weaker, right? So these three important pieces of information we can get immediately without significant efforts. Again, perpendicularity, downhill, and proportional to the density of lines, all right? Okay, so now let's prove quickly this perpendicularity. Let's prove this. And so what do we have to use in order to prove that? First of all, you see we're trying to get information about the electric field from the electric potential. So we have to use this bridge, which is, where is it? Here. E sub s equals to minus dv over ds. We proved it in the past, right? And when we derived this formula, S direction was a completely arbitrary direction. S can be this direction, any direction, right? When we derived it, S was a completely arbitrary. So we have a freedom to choose, to align S along any direction, okay? So let's see. Oh, guys, somebody's mic is whistling, right? So let's align direction of S along an equipotential line, right? So S along equipotential line. For example, along this V minus, right? So let's say this is our S direction. And where along that direction, of course, what happens with V? It stays constant. V is constant along equipotential line. So as a result, what can you tell about this dV? Of course, it's zero, because V doesn't change, and dV, it's a change in V. If electric potential is constant, then of course dV is zero, and then of course you can say that dV over ds is zero, and of course the S component, which is basically component of the electric field along equipotential line, is zero. Component of the electric field along equipotential line is zero. So it's impossible to have a component of the electric field along an equipotential line. So if that component is not possible, what's left? Of course, perpendicular. So if there is an electric field, of course, it can be only perpendicular to the equipotential line. You see, the proof is quite simple, right? Quite simple. So just from now on, you remember electric field all the time perpendicular to the equipotential lines, points downhill, and the strength of the electric field is proportional to the density of lines. Larger density, stronger field. Smaller density, smaller field. A weaker field. Right. Okay, and now after this, let me give you this second clicker question to practice this. right? Okay, let's here's the question. So let's assume that we have some electrical aura, right? Which is described by this, you see, electric field vectors, right? So you see it points this way. Here electric field is weaker, then it's getting stronger, and the strongest. And of course, we can also describe this electrical aura using equipotential lines, using electric potential. And you see we have 6 options, 6 possible options. So which option of these equipotential lines matches this electric field? So which equipotential lines describes exactly the same electrical aura as this electric field does, right? So you see option A, you see here 0 volts, then 50 volts, then B and C and so on, right? Okay, give it a try. It's directly connected to what we just discussed. Right. Again, so now it's a question 2, right? Again, if you scroll it up, it's just a conceptual test number 2. And you will try. A few times in the past, I give a question similar to this on one of the exams. I think it's on the second midterm exam. Okay, all right, let me look at your answers. I see your answers. Okay, I like the trend. Okay, as far as I remember, this was the number of answers in the previous question. So, no more. Okay, so now let me discuss it. Okay, good. Nice distribution. So, let's apply it. I mean, these results which we just discussed. And let's start with option F. I would just want to discuss all of them. Let's start with the this last one. So first of all, you remember electric field must be perpendicular to the equipotential lines. Okay, and of course, it's correct for all of these 6 options, right? So all these equipotential lines are perpendicular to the direction of the electric field. So that's correct for all of these. Then downhill. Right, electric field must point downhill in the direction of decreasing V. So in option F, downhill, so here we have potential 50, over there potential 0. So downhill it's that way. So electric field must point that way, which is obviously the wrong direction. Then what about the strength? Density of equipotential lines here larger, so it means that electric field must be stronger. And then it goes down that way. So as a result, we're getting, okay, let me bring forward these slides. Okay, so it means that here electric field stronger, then it gets weaker and weaker, and of course points downhill that way. So it's obviously not our case. Now E, option E. Downhill, it's still the same direction, right? Because here we have 50 volts, there 0 volts. Then density of lines gives us strength of the field. So here density is weak, so electric field must be weak. Okay, density is small, electric field is weak, right? And then it's getting stronger and stronger that way. So we're getting a weak field, stronger, and the strongest. Again, not our case, right? Because direction is wrong. Right? So then, D, what can you say about this electric field immediately? We have even special term to describe electric fields like this. It's called uniform electric field, right? Uniform electric field, right? Because you see, density of lines exactly the same, so it means that electric field strength the same. And then, of course, direction will be also the same. Of course, direction is downhill. Here, electric potential higher, there lower, so downhill is that way, right? So it's a case of the uniform electric field. So it's not our case anyway. So then option A, again, uniform electric field, but pointing in the opposite direction, because downhill it's that way. Right? Again, not our case. Now C, let's discuss case C. Again, downhill it will be, direction will be correct, it will be that way, right, downhill. Then density of lines here stronger, it gives the electric field here, electric field will be stronger here, and then it will get weaker and weaker. So we're getting a right direction, but wrong strength, electric field strength. Okay, and the last option left, B, which must be correct probably, right? So downhill that way, and that is the correct direction, right? Matches our direction, needed direction. And then strength, density of lines here larger, so electric field stronger, right? And then density gets smaller and smaller. Of course, electric field gets weaker and weaker, right? And of course, we're getting the correct field. So option B is the correct answer. Right? Option B is the correct option. Is the correct option. So that's how we can visualize that electrical aura using electric field, and that's how we can visualize that electrical aura using equipotential lines and using electric potential. Okay, as I said, yeah, a few times in the past I gave a similar question. Of course, I can change slightly, right, on the exam. Right? But of course, this material is not going to be on our exam number 1. Right? Okay, so now we can move the next. You remember electric properties of conductors. We spent like the whole lecture discussing them, right? So you remember if a piece of a conductor in the electrostatic equilibrium, if this conductor has any excess charge, that excess charge must be on or can be only on the exterior surface. Then electric field inside of the conductor must be 0 all the time, right? Again, in the electrostatic equilibrium, right? And the electric field outside of the conductor must be perpendicular to the surface, right? Now we introduced electric potential. So what can we say about the electric potential, for example, inside of this conductor? So now, since we introduced new quantity, we need to add an additional property of a conductor, again, in the electrostatic equilibrium. Right? Okay, so since we have plenty of information about the electric field and we want to get information about the electric potential, we have to use the proper bridge, which we derived in the previous lecture, that integral, right, which allows us to move from the electric field to the electric potential. And let's recall it. This is the bridge, right? And in order to apply this bridge, of course, we need to pick some initial point, the final point, some line along which we're going to integrate. Okay, let's do it. We don't have any other options. So let me pick completely arbitrary initial point and completely arbitrary final point. You see, this is initial and that is the final point. And completely arbitrary path along which we have to integrate this dot product of E and ds. Who can see what will be the value of this integral immediately? What will be the value of this integral? It will be, of course, 0, because electric field inside of the conductor is 0. Basically, we're integrating a 0 function. If you integrate 0 function, of course, you will end up with the 0 integral, right? So immediately we can say that delta V inside of the conductor is 0. And of course, then the next logical question, so conclusion, general statement, what can you say about the electric potential inside of the conductor after this? Again, during the normal semester, of course, I ask students, right, in the lecture hall, and most of the time, students answer this. They say that electric potential inside of the conductor is 0. Not completely correct. Okay, not completely. Okay, it can be true under certain conditions, but we need to make a statement, more general statement. We came to this conclusion that delta V equals 0, right? If, for example, final point is at 5 volts and initial is at 5 volts, we're still getting 0. Delta V is 0, right? So the most general statement that we can make at this point, we can say that electric potential inside of the conductor is constant. Electric potential 0, yeah, it's possible, but under certain conditions, it's a special case. General statement that electric potential inside of the conductor is constant in the electrostatic equilibrium. All right. Okay, so now we're adding an additional property of a conductor, that electric potential inside of the conductor is constant, right? Okay, then what can you say about the surface of the conductor? You see this exterior surface of the conductor. What can you say about that surface? Since potential inside of the conductor and of course on the surface is constant, so we can say that that exterior surface is an equipotential surface. All the time, if you have a conductor in the electrostatic equilibrium, its exterior surface is an equipotential surface, right? Or in this case, sort of like a two-dimensional picture, right? We can say it's an equipotential line, right? Okay, so that's an additional piece of information about the conductor. And now, at this point, we can say goodbye to electrostatics, basically. Right, let me check. Yeah, goodbye to the electrostatics. And from this point, we'll start moving slowly to some kind of a dynamics where we have electrons drifting, giving us current. So we'll start slowly moving towards simple circuits. Simple circuits, right? And from this point, and of course, yeah, in order to move to simple circuits, of course, we will start introducing the simple elements, right? So like a battery, then resistor, then capacitor, right? Stuff like this, so that we can play with the circuits. And another thing, so up to this point, almost every class I will tell, okay, so let's introduce a new fundamental law. Almost very often we've been introducing new, more and more fundamental laws. And from this point, for quite some time, we're not going to introduce any new fundamental laws, because this simple circuitry, which we will start discussing, it's just application of those fundamental laws in circuitry. Of course, we're going to introduce some new quantities, new parameters, but those are not going to be something fundamental. Now, it's just basically application of the fundamental stuff which we introduced in the past, like electric force, electric field, right? Some other stuff. So now for quite some time, you're not going to hear from me, okay, so this is something fundamental, right? Okay, so anyway, so now, from now on, for maybe 4 months or so, we will be discussing simple circuits. Again, from the point of view of physics. Of course, guys, from EE department, you know much deeper, right, from the practical point of view, circuitry. But we're going to discuss from point of view of physics. Right? Okay, so, and of course, first element must be a battery, electric battery, so that we can drive current through simple circuits. And of course, the world of batteries is very deep, and of course, I don't know the whole depth of that world. So as a result, we will discuss a simple basic idea of how battery works. Okay, so let's assume that we have some jar and filled with some aggressive acidic solution. Of course, you have to find the proper solution, right? And then let's take 2 electrodes. One is made of carbon, the second made of zinc. Submerge them, and of course, this acidic solution will start interacting with these electrodes. So let's start with zinc electrode. Of course, there will be some chemical reaction, right? Atoms of zinc will start interacting with that acidic solution, And during that chemical reaction, of course, atom of zinc atoms of zinc get dissolved, right? Some chemical reaction. And during that chemical reaction, atom of zinc gets dissolved and leaves behind 2 electrons. So it leaves this electrode, right, as a positively charged ion, right, leaving behind 2 electrons. That's what happens during that chemical reaction. So basically it's stripped with 2 electrons, right? Okay, so now this atom of zinc, free to wander, and of course it will start drifting around, right? And sooner or later it will end up near this carbon electrode. And carbon electrode is very generous in terms of giving electrons. Okay, so it looks like you're poor thing, you don't have electrons. Okay, here's a couple for you, no big deal, right? Very generous. So when this ion of zinc comes to carbon electrode, it can easily get 2 electrons from this carbon electrode. As I said, carbon is very generous, right? So of course you need to pick these materials, proper materials. So atom of zinc, ion of zinc gets these 2 electrons, becomes neutral, and gets drowned, goes down to the bottom of this jar, right? And as a result of this drift of only 1 atom of zinc, this electrode becomes slightly positively charged. This electron becomes slightly negatively charged. But of course, it happens not just to 1 atom of zinc. It happens to gazillion number of atoms of zinc, right? As a result, this electrode will be significantly positively charged. This electrode will be significantly negatively charged. And so now you have potential difference. You can connect wires, and you can create the potential difference across the circuit. And of course, current will start flowing. Right? So that's the basic idea of how battery works. And of course, from the philosophical point of view, we can say that what happens in the battery? Battery just converts energy of chemical reaction into electrical energy, right? Into the electrical energy. Of course, in a month or so, we will see that we can also create electrical energy. We can convert mechanical energy into electrical energy, which can be more practical, but that will be in the future when we get to Faraday's law. But for now, we're going to use battery, where energy of chemical reaction gets transformed into electrical energy. Okay, so that's sort of rough description of how battery works. And now we can say, yeah, we can now, from this point, we can legitimately use batteries in our simple circuits, right? So next element which we need to introduce is a capacitor, all right? Very important. And usually at this point I would ask, okay guys, so what's the major role of a capacitor in any circuit? And usually students answer that the major role, of course, is to store charge. And that's absolutely correct. Nothing wrong with that, right? Yeah, it stores energy. I mean, it stores charge, and then the charge can be reused. But you know what? I usually prefer to state the major role of a capacitor in a slightly different way. And I will explain why. Right? I usually say capacitor is a device which allows us to store energy in the form of the electric field. Why I prefer this way? Because maybe like in a month and a half, we will introduce inductors. And inductors, the role of inductors in the circuit, in a circuit, is it allows us to store energy also, but in the form of the magnetic field. So the role of a capacitor and the role of an inductor are very similar, but this plays a role, it's a role in the world of electricity. An inductor plays the same role in the world of magnetism. Yeah, in the world of magnetism. So capacitor allows us to store energy in the form of the electric field, Inductor allows us to store energy in the form of the magnetic field. So that we can compare these two elements, I usually prefer to use this state the role in this form. It allows us to store energy. And then, of course, later you can use that energy a few milliseconds later, right? Creating some oscillating systems and so on, right? So it allows us to store energy. Okay, so that's sort of the role, but what about strict definition of what of how we define capacitance, right? Okay, so let's assume that we have two pieces of metal. Here's one and there's the second one, right? And so how do we usually charge them? So in order to charge them, we can just take 100 electrons from this piece of metal, 100 electrons, for example, and move them to that one. As a result, this, now I can call it electrode. Now this electrode will be positively charged, and that will be negatively charged. And absolute value of the charge will be exactly the same. So that's how we charge the capacitor. We just move some electrons from one electrode to the other one. As a result, in absolute value, they have exactly the same amount of charge. 5 coulomb minus 5 coulomb, 3 coulombs minus 3 coulombs. Every time, absolute value of the charge is the same. Okay? So now, let's introduce the definition of capacitance. Okay, so let's assume that we moved some amount of electrons, right? So this is charged and that one is charged. And of course, there will be some potential difference between these two electrodes. Of course, there must be potential difference because here potential is positive, there potential is negative, right? Of course, potential difference will be there. Okay, so then what if we increase amount of charge? What will happen to the potential difference? Of course, it will go up as well. You increase charge more, potential difference will increase. And if you keep playing by increasing charge, of course, potential difference increases as well, right? And of course, the natural desire, what about the ratio? If both of them increases at the same time, charge and the potential difference, what if we look at a ratio of charge versus the potential difference? And if you look at that ratio, you will be surprised that within experimental error, that ratio stays the same. Okay, so if it stays the same, and of course, assuming that you don't change the system, right, except for increasing charge or decreasing charge, if you keep the system the same, so it basically it means that that ratio is some intrinsic property of this system. Intrinsic property of the system. So let's give it a cool name, and that name is capacitance. Capacitance, by definition, is the ratio of the charge versus the potential difference. Some students ask, are we adding the charges or subtracting? So what does it mean, this charge? It's just a charge, think in this way, it's just the charge of the positive electrode. Or you can say just the absolute value of the charge of one of the electrodes. Charge divided by the potential difference between electrodes. This is general definition of a capacitance, right? And of course, now, since we introduced a new quantity, should we introduce the special unit for that? And yes, it makes sense because capacitance is used a lot. Everyone, starting from technicians, engineers, right, experimentalists, everyone uses capacitance a lot. And instead of pronouncing every time that I have a capacitor of, let's say, 5 coulombs per volt, 7 coulombs per volt, every time pronouncing this coulombs per volts, it can be really annoying. And in order to make the life of those people working with capacitors a little bit easier, of course, it makes sense to introduce a special unit, farad. So I have 5 microfarad capacitor or 7 microfarad capacitor, right? And so on. So it makes sense to introduce the special unit, farad, to make their life easier. And of course, the last piece which I want to say before we'll finish it. Again, it's a general definition of capacitance. You can apply it to find capacitance of any object. Parallel plate capacitor, we'll do it probably in our recitation class. Cylindrical capacitor, spherical capacitor. You can probably find capacitance of me, right? But of course, once you start dumping some charge on me, of course, you will realize that on top of the fact that I have capacitance, I have some resistance, because I'm not going to like the fact that you're going to dump charges on me, right? So basically, again, you can apply it to find capacitance of anything. Of course, the first point, we're going to apply this formula to find capacitance of a parallel plate capacitor. Okay, sorry for holding you extra a minute.